The classical planetary model of the atom, with electrons tracing rigid orbits around a nucleus like a miniature solar system, is mathematically obsolete and physically inaccurate. An electron does not possess a physical trajectory. Its state is actually defined by a three-dimensional probability distribution. Yet we can map these seemingly chaotic probability regions perfectly. We do this using a strict mathematical address system. This address consists of four specific variables: the quantum coordinates, represented mathematically as n, l, m sub l, and m sub s. By the end of this analysis, we will use only these four integers to derive the exact structure of an atom from scratch. The first coordinate is the principal quantum number, n. It dictates the main energy shell and the overall geometric scale of the orbital. The value of n must be a positive integer. The maximum electron capacity of any given shell is strictly dictated by the formula 2n squared. The second coordinate is the azimuthal quantum number, L. This integer defines the geometric shape of the subshell. This 3D model shows the physical rendering of L equals 0, the s orbital. It is spherical, non-directional, and its physical size scales up as the principal shell number expands from 1s to 2s to 3s. When L equals 1, we get the p orbital. The geometry shifts into a highly directional, dumbbell-shaped volume. To define how this dumbbell sits in space, we introduce the third coordinate, the magnetic quantum number, m sub l. For p orbitals, m sub l dictates three degenerate spatial forms arrayed along the major axes. When L equals 2, the d orbital emerges. Four of its 5 distinct orientations take a double dumbbell shape. The single major geometric exception is the dz squared orbital, forming a single donut-shaped electron ring running strictly along the z-axis. The combination of n, l, and m sub l provides the complete spatial definition for every possible region an electron can inhabit. An electron's probability density is not a solid block. It contains internal structural gaps. These absolute zero probability zones are called nodes. They bound the internal geometry as the energy level scales up. Radial nodes are concentric spherical gaps between successive shells. We calculate their exact quantity using the formula n minus l minus 1. Angular nodes are flat planar or conical cuts passing straight through the nucleus. The number of angular nodes is equal exactly to the value of L. Applying the formulas to the 3p orbital row in this table proves the math. With n equaling 3 and L equaling 1, the formula yields exactly one radial node and one angular node. This cross-section shows what those gaps actually look like inside the boundary. There is exactly one spherical empty gap, the radial node, and one flat slice bisecting the middle, the angular node. The architecture of an atom is defined just as much by the empty voids where an electron cannot exist as by the regions where it can. Shifting perspective from spatial geometry to pure energy, we find that in a single electron system like hydrogen, energy relies solely on the principal number n. In multi-electron systems, shielding effects and interelectronic repulsions shatter that simple symmetry, forcing energy levels to depend on both n and l. This sequence is governed by the Bohr-Bury rule. Orbitals are filled in a strict ascending order of their combined n plus l value. If two distinct orbitals share an identical sum, a tiebreaker is required. The 3p and 4s orbitals both total an n plus l value of 4. The orbital with the lower n value, in this case 3p, is more stable and fills first. Comparing 4s to 3d, the 3d orbital totals an n plus l value of 5. Because it has a higher net energy, the 3d shell fills after the 4s shell, despite possessing a lower principal number. This math establishes the Aufbau principle. Electrons completely populate lower available energy thresholds before occupying higher subshells. This chart visualizes that exact sequence mapping out. The energy bars populate in strict ascending order, climbing from 1s to 2s, 2p, 3s, 3p, 4s, and then 3d. Atomic filling is not a chaotic stacking process. It is a strictly ordered mathematical climb, dictated by the sum of n and l. The placement of electrons into this sequence requires the fourth and final quantum number, spin, or m sub s.
It defines the electron's intrinsic rotation, which can only be +1/2 or -1/2. The Pauli exclusion principle states that an individual orbital cell can hold a strict maximum of 2 electrons. Crucially, those electrons must possess opposite, anti-parallel spin orientations. We apply these constraints to a complete element, using nitrogen, atomic number 7, to understand the filling of degenerate subshells. Hund's rule of maximum multiplicity dictates that electron pairing cannot take place until every orbital in a degenerate subshell contains one single electron. If an electron is paired too early in the 2p shell, it violates systemic energy optimization. Forcing 2 electrons together creates excessive interelectronic repulsion. The ground state requires strict separation. Singly occupied orbitals must maintain parallel spin orientations, pointing in identical directions to maximize stability. Electrons act less like solid objects and more like a highly ordered fluid, filling lowest energy voids and avoiding each other until mathematically forced to pair. Mapping these one-dimensional mathematical rules directly back into physical space, the linear energy sequence folds up into a complex 3-dimensional probability cloud. The hierarchy is absolute. The principal number n defines the scale. The azimuthal number L carves the geometry and nodes. The magnetic number m sub L sets the spatial orientation, and the spin number m sub S caps the population. Every electron obeys 3 strict laws: the Aufbau sequence of ascending energy, the Pauli exclusion of opposite spins, and Hund's multiplicity of maximum separation. By calculating the physical shape of probability, we have defined the specific quantum coordinates that dictate how every atom is constructed.